All right. Hello, everyone. Hope you're doing well. Time to do 5 simple, useful, but very hard probability questions. I hope you're here for it. So, let me know if the music is too loud. Let me know if you can hear my voice. If there's any issues with the stream, just let me know. And if not, we can get started. So, hello, Hitoshi. How are you? So I was thinking we can... Actually, maybe the music is a little too loud. So I was thinking I could state the problems first, and we can go from there. So I already have a problem up on the screen. I don't know. Let me know the order in which you would prefer to go. If you want me to state all the problems, like state a problem. Hello, Petros. Petros, sorry, I said your name wrong, but I hope you're well. So I don't know how you want me to go. If you want me to state all the problems and then do the solutions afterwards, or if you wanted me to go problem, solution, let me know. I picked these so that they would have short answers, but they're not particularly easy probability questions. So I already have one up on the screen, which is 2 real numbers x and y are chosen at random in the interval 0, 1. Compute the probability that the closest integer to x over y is even. So that's one of the problems. Okay, so here's another one. Probably one of my my favorites here. So 100 people line up. Hold on, let me make sure I'm not like in my own way. So 100 people line up to board an airplane. Each has a boarding pass with an assigned seat. However, the first person to board has lost his boarding pass and takes a random seat. After that, each person takes an assigned seat if it's unoccupied, and one of the occupied seats at random otherwise. What is the probability that the last person to board gets to sit in his assigned seat? Okay, so... also, let me know if there are any questions about these problems. I mean, I tried to get rid of any of the like faff in these problems. So the first problem that you see above was from a Putnam exam, and the second problem here is from Peter Winkler, who's a legendary kind of puzzle, like math puzzle person. He's published a number of fantastic math puzzle books. So that's a source for the second one. I believe you can find, the first problem is on a Putnam exam. I forget the year. The second problem is from this book called Mathematical Puzzles: A Connoisseur's Collection by Peter Winkler. You can find it there. Okay. So hopefully that makes sense. Let me put down the next problem. So another deceptive one, but here's another one. So choose at random 3 points on a circle. It's a unit circle, so x squared plus y squared is equal to 1. And you can interpret the points as cuts that divide the circle into 3 arcs. And you just want to compute the expected length of the arc that contains the point 1, 0. Okay, simple enough. You have a circle, you divide the circle into 3 arcs, and you want to compute the expected length of the arc that contains the point 1, 0. Okay, there you go. All right, let me just put the next problem up. So I really love this. I mean, I love them all because I picked them all, but I do like these problems a lot. So let alpha in 0, 1 be an arbitrary number. And you have an unfair coin with a probability p and 0, 1 of being heads. And your task is to design a game between Alice and Bob so that Alice's winning probability is exactly alpha. So you have a device to generate randomness. Okay, you have a device to generate randomness, and it can basically you have the probability of getting heads. So you basically have a random number generator that gives you 1 or 0. And it gives you 1 with probability p, it gives you 0 with probability 1 minus p. And you want to use this device that you have, okay, to create a game that has a probability precisely alpha, okay? Where the probability of winning is precisely alpha. Now, I will say this to you. if you have trouble with this question, try doing the version where you have a fair coin, okay? So imagine you have a fair coin in your hands. How would you use the fair coin to create a game where the probability of winning is precisely alpha? Okay. All right. So now, unfortunately, I'm running out of room a little bit, so I'm going to have to delete these. Let me know if you have any questions about any of these. I'm just going to delete these. And then the final question I have for today, as I said, I have 5 questions, is going to be, let's see, which one haven't I done yet? Oh, yeah. So there's this one. So there's 64 teams playing in a single elimination tournament. There's 6 rounds. So if you've ever participated in like a basketball bracket prediction thing, I forget what they're called. But there's 6 rounds, and you have to predict the winners for all 63 games. As you know, it's extremely unlikely that you would do this. But here's the thing. Instead of only winning things if you get everything right, you're being scored on a point system. So you get 1 point for every correct prediction in the first round, 2 points for every correct prediction in the second round, 4 points for every correct prediction in the round after that, 16 points for every correct prediction in the round after that, and 32 points if you correctly predict the final. And so the question is, what is going to be your expected number of points here? What is going to be your expected number of points? Okay, those are all of the probability questions. Let me know if there are any issues with these. Let me know if there are any preferences as to which problem you would like to see the solution to first. Okay, all right. So if nobody has any preferences, I'll probably start with the problem that I have up here, which is 2 real numbers, x and y, are chosen at random in the interval 0, 1. Compute the probability that the closest integer to x over y is even. Now, I do want to say that if you don't want spoilers for these problems and you're watching the VOD later, this would be a good moment for you to pause the video, leave, and come back in order to get the solutions. Okay? All right. So, because at this moment I'm about to dive in if there are no other questions about any of this. Okay. So let's do the first problem. 2 real numbers, x and y, are chosen at random in the interval 0, 1, and you want to compute the probability that the closest integer to x over y is even. Okay. In order to do this problem, you have to first ask yourself the question, sort of, what exactly does it mean for the closest integer to x over y to be even? Like, kind of, how do you algebraically state? So Petros Paulus says 0.4645. Trying to think if that's I mean, I do know the answer. Let me just I know the exact answer, so I'm just gonna type it in a calculator and see how close you are. Just give me a sec. I'll do it off screen so I don't reveal the answer to everyone else. But let's see. So it's I remember on a previous video, integer closest. Wow, that is very good, Petros. It seems like you may have done a numerical simulation here. Okay. So neither ceiling nor floor, closest integer. So you want the integer that's within less than 1/2 of this fraction, Nishant. Does that make sense? So for example, if x over y happens to be, I don't know, 0.6, right? Then the closest integer to this is 1. But if x over y happens to be 0.4, then the closest integer to this happens to be 0. Okay? All right. So hopefully that makes sense. As to Petrus, your numerical simulation worked. It's off by a little bit. If you look at the decimal expansion, I think it's 0.4646. Yeah. So, yeah, exactly. Round. Okay, so here. So, okay. If there are no other questions about this, I'm about to dive into the answer. So let's go. So how might you do this problem? This is kind of an interesting problem with an interesting answer. So here's what I'm going to do. I'm going to take all of my possibilities for x and y and just draw them in a nice, neat little square. Okay? Also, I would like to algebraically express the condition that the integer closest to x and y, to x over y is even. So I want the integer closest to x over y is even. What does this mean exactly? Okay. Let's say that the integer closest to x over y can be written as 2 times n. A reasonable thing to do. If it's even, I can write it as 2 times n, where n is some integer. Right? My gut feeling says that it would be greater than 50% for, that's odd. It's close to 50%, but it's definitely not greater than 50%. So Petrus Paulus's numerical simulation got close to the answer. But let's see how you would actually tackle a problem like this. So let's say the integer closest to x over y is 2n. What does that mean exactly? Well, that means, of course, that x over y must be kind of nuzzled in between 2n plus a half and 2n minus a half, right? That's what it means for x over y to be closest to 2n above all other integers, right? Now, if that makes sense, what I can do is I can break this down and express this as 2 inequalities, right? So I can write this as, how about this? 2n minus 1/2 is greater than x over y, and 2n minus 1/2 is, is less than x over y, and 2n plus 1/2 is greater than x over y. Agreed? That's what this is saying. Now what I can do is I can basically manipulate this, and I want to write these as equations that I'm more familiar with, like equations for lines. And so this will give me, in fact, that y is, because x and y are both positive, I can multiply and divide by x or y on either side of the equation without too much issue. So basically, y is going to be less than x over 2n minus 1/2, right? And this other equation is going to give me that y is in fact greater than, let's see, x over 2n plus a half. Agreed? So let's put these two equations together now that I have derived. So in fact, y is less than this number, and y is greater than x over 2n plus a half, right? Let me know if there are any questions about this. I might take the common denominator just to make this a little bit easier on myself. So if I take the common denominator over here, it's going to be 4n plus 1 over 2. So I can write this denominator as, so I can just write this as like that, right? Hopefully that makes sense. And then I can take the common denominator here, and I would get 2x over 4n minus 1. Seem reasonable? So basically, these types of equations should be fairly familiar to you guys. Basically, this is the area between two line segments, right? This is just the area between two line segments, essentially. And so, for example, let's see what this equation is saying when n is equal to 0, Okay, let's examine that first. Let's look at these equations when n is equal to 0. Now, when n is equal to 0, it's basically saying that y is between kind of negative 2x and 2x, right? Which is essentially telling me that, well, I don't need to worry about the line negative 2x, right? Only the line 2x matters here. So if I graph the line y equals 2x, right? This is the line y equals 2x. It intersects here at x equals 1/2. So x over y chosen in this entire region would satisfy the constraints that x over y is even. Let me know if that makes sense. So this is what it looks like if you just examine what these equations are saying when n is 0. Okay? What do these equations say when n is in fact equal to 1? Right? When n is equal to 1, these equations are saying that y is nestled kind of in between these two lines. And so the lines are going to be 2/5 x, and this one is going to be 2/3 x. Agreed? So 2/3 x will, when x is 1, y is going to be 2/3. So when n equals 0, you get this condition. So 2/3 and 2/5. Hopefully that makes sense. Is the probability, they are uniformly distributed independent random variables. So the issue is that having an even number be closest to x over y is not a perfectly like symmetric condition, right? So as you can see, the area, if you add up all these triangles, I guess I'm just gonna jump the gun over here. So basically, if you write down all of the resulting equations, so you're gonna get y is between 2/5 and 3/5. For the next one, you're gonna get that y is between kind of 2/7 and 2/9 x, and for the next one, you're gonna get that y is between 2/11 x and 2/13 x. Hopefully the pattern is making sense. So essentially you need to add up the areas of all of these triangles over here, right? So the area of this triangle, well, its base is 1/2, right? And its height is 1. So the area of this first triangle in here is going to be 1/4, okay? By the way, let me know if there are any questions about anything I've done so far. So essentially, for x over y to be closest to an even integer, any of the following conditions can be satisfied, and you can compute the probability of these happening by adding up the areas of all of these triangles. So essentially, there's going to be another triangle in here where you're between 2/7 and 2/9, right? And then there's going to be another triangle even smaller still, where you're between 2/11 and 2/13, and so on and so forth. And you just essentially need to add up the areas of all of these triangles. Okay, so if I look at the area of all these triangles, the area of this triangle is 1/4, right? The area of this next triangle is 1/2 times 2/3 minus 2/5. Agreed? Because the base of this triangle is 2/3 minus 2/5, and the height of this triangle is 1/2, right? And the area of the next triangle is going to be 1/2 the next one is going to be 2/7 minus 2/9, right? And the area of this next triangle is going to be 1/2 what would it be? 11/13, and so on. and so on and so on it goes. So the probability here is going to be the sum of this series. Okay. Now this series converges. You can check via the alternating series test. I'm going to simplify it a little bit. So you can cancel out a lot of these 2's, right? So this 2 will cancel with these 2, blah, blah, blah. All the 2's will cancel out. So essentially you get a quarter, which is a little weird. What was it again? A quarter plus a third minus a fifth, right? You get a quarter plus, the quarter is kind of weird and special. Let's deal with it separately. But it's a quarter plus a third minus a fifth plus a seventh minus a ninth plus an 11th minus a 13th and so on. So hopefully the pattern here is relatively clear. And let me know if that does or does not make sense. Okay. Does anyone recognize this? So by the way, the alternating series test is enough to tell you that this converges to a specific value. But if you're familiar with this series before, you might also remember, this might also be somewhat familiar to you. So you might remember, for example, that if you do 1, I believe minus a third plus a fifth minus a seventh plus a ninth minus 11th plus a 13th and so on, I believe it is, this is pi over 4. Okay. Zusa is very close. So no, pi squared over 6, Nishant, is when you do the sum of the reciprocals of all the squares. So pi squared over 6 is like, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on and so forth. In any case, this is a pretty famous series, I believe. It's okay if you haven't seen it before, but it's a fairly popular and famous series. And so essentially pi is going to equal 1 minus a third plus a fifth minus a seventh, and so on. So yeah, it's the basal problem. But this one is not the basal problem. You can get this one from the Taylor expansion for arctan or something like that. This one is not so bad at all. And so if pi over 4 is equal to this, remember what we were interested. Actually, I shouldn't have erased it. So we were interested in this series, right? So this second half here, this whole bit here, is just 1 minus pi over 4. Agreed? The second half is 1 minus pi over 4. So the final answer is going to be a quarter plus 1 minus pi over 4, which is 5 minus pi over 4, I believe. If I'm not. Yeah, it should be 5 minus pi over 4. It's going to be the answer to this question. Kind of neat, huh? Okay. So let me know if that makes sense. And if it does make sense, I will now move on to the next problem. So if there are no more questions about this, I will proceed forth. Okay. Let's do the next problem that I have picked out. Let's do the airport problem, just because it's super weird. I'll give you guys a second to think about it. You have not, well, you missed just the first problem, but there's still 4 more to go. Ken, I hope you're well. I do love this one, so you've arrived at a great and fantastic time. I'll reread the problem. So 100 people line up to board an airplane. So you can imagine there are 100 seats on this airplane, okay? And each has a boarding pass with an assigned seat. So there's a person assigned to seat 1, there's a person assigned to seat 2, all the way up to seat 100. So the first person necessarily sits at a random seat. So the first person does not occupy their own seat, and they take a random seat. Okay. So the first person does not occupy their seat. You've seen this one? Okay, very good. And they just take a random seat. Okay. After that, each person takes an assigned, like their seat if it's unoccupied, but if it is occupied, my camera's covering the text. Darn. Okay, let me, there you go. I'm just gonna put it down here. Okay, so I hope that's good now. So 100 people, okay, so basically everyone will take their own seat if it's not already taken, and if their seat's already taken, they're just gonna pick a seat at random and get into it. And so the question is, what is the probability that the last person to board gets to sit in their assigned seat? That is the question. So let me know if you guys have any issues with this. I will dive into the solution of this momentarily, okay? So this is the question. The first person does not sit in their own seat, and every subsequent person sits in their own seat if they can, but if not, they pick a seat at random. Okay. What is the probability that the last person will get to sit in the seat that they were actually assigned? Okay. This problem, somewhat miraculously, the answer to this problem is 1/2. How cool is that? So 1/2 is the answer to this question. And it turns out it's very easy to see if you think about the problem the right way. And of course, very hard to see if you think about the problem the wrong way, okay? If you sit here trying to do like, thinking about all the possibilities and analyzing who sits in what seat, you're gonna run into a lot of trouble kind of remarkably quickly, okay? But there's an observation I would like to make here that's kind of surprising that I believe will simplify the problem tremendously, okay? So here's the observation I want to make for you. The last person is going to sit in their assigned seat if it's unoccupied. Agreed? Those are the rules. The last person must sit in their assigned seat if it is unoccupied. Okay? However, there should be, so in order for them to not sit in their assigned seat would have to be occupied. So my question is, if the final person's assigned seat is occupied, can you tell me what the unoccupied seat would be? So this is my question to you, okay? So if the last person's seat is occupied, what is the unoccupied seat? I'm sorry, I didn't mean unoccupied. If the last person's seat is occupied, what is the unoccupied seat? This is my question to you. So this is my mega massive hint to you. So let's say the last person walks in and their seat is in fact occupied. What can you say about the unoccupied seat? Okay. Very interesting. I'm going to make a claim here that took me by surprise when I first heard it. If the last person's seat is occupied, then the unoccupied seat must be the first person's seat. So the answer to this question is it has to be the first person's assigned seat. Why? Why is this the case? How come if the last person's seat is occupied, then the unoccupied seat has to be the first person's seat? If you see this, it's not that hard to see that the answer is 1/2. So basically, this is what I'm trying to explain to you, okay? Why this is the case. Move this over just a little bit. Okay, what if it's not the first person seat? Okay, let's say the last person walks in, okay, and their seat is occupied, and let's say number 27's seat is the unoccupied seat, because there has to be an unoccupied seat, right? If the final person's seat is occupied, there are 99 people seated, there has to be one unoccupied seat when the last person walks in, right? If the last person walks in and their seat is occupied, and let's say seat number, person number 27's seat is unoccupied. Well, if it's unoccupied now, no one must have taken that seat through the entire process. Agreed? No one must have taken that seat through the entire process. If seat number 27 or whatever is unoccupied at the very end, then that means it's been unoccupied the whole time. No one took that seat. But then the question is, what was person 27 doing then? Right? And you can apply that logic for every single seat. So if, for example, person number 3's seat was unoccupied, then it must have been unoccupied the whole time. But then what was person 3 doing when they showed up? Remember, if seat number 3 was unoccupied when person number 3 showed up, person number 3 had to take person number 3's seat. And the same thing is true for now and forevermore, right? So the last person's seat is occupied. The unoccupied seat has to be the first person's assigned seat. Okay? But now the problem is basically solved, because every person that shows up has no preference. So every person who must choose a random seat has no preference between all available seats, right? So in this scenario, when the last person shows up, right? Also, at each point, either person's seat is available, or only seats higher than that person's seat are available, except seat 1. That's also true. That is another way to think about it. That's absolutely true. But essentially, when the kth person shows up, they have no preference between seat 1 versus the first person's seat and the 100th person's seat. They have no preference. At no point does anyone have a preference between those two seats, which means the probability between those two seats is always the same, which means the final probability is precisely 1/2. Okay? I love this problem. It's extremely counterintuitive, though. But I hope that makes sense. And please let me know if there are any questions about this as well. If not, I would like to move on to the next problem. Okay. Let's move on to the next interesting and exciting problem. Okay. This one's really weird. I hope you're ready for this. Okay, I hope I'm not covering it up again. I am covering it up again. Hold on. Let me do some problem surgery very quickly. Beautiful. Oh. Okay, I did not want to do surgery that way. Here, let me put this lower. There you go. Beautiful. I'm a expert problem surgeon here. I know you're all in love with my work here. So let alpha in 0, 1 be an arbitrary number. The only randomizing device that you have is an unfair coin with probability p in 0, 1 of heads. And your goal is to design a game between Alice and Bob so that Alice's winning probability is exactly alpha. Okay? So, let me, while you guys think about this, I might exert even more of my paint energy and see if I can't fill out these gaps. Why isn't this working? So I don't want to. I want a filled rectangle. Okay, you know what? I'm just gonna try and make this look a little bit nicer. And in the meantime, I would like you all to think about this exact problem. Okay. So your goal is to use this unfair coin that has probability P of landing heads. And you want to design a game where the probability of winning is exactly alpha, where alpha is a number you have no control over. It's a number that I hand you in this situation. Okay? If you're struggling with this, try to do it with a fair coin. How might you use a fair coin to design a game where the probability of winning is precisely alpha? How would you do this? While I continue to surgically alter my problem to look a little bit nicer on a screen that you cannot see. Okay. Come on, that's a beauty right there. Oh no, I know, I need to... No, the magic power of paint takes us to victory again. Okay, so this is the question. So alpha in 0, 1 is an arbitrary number, and you have an unfair coin. You want to design a game so that Alice's winning probability is exactly alpha. How would you do this? How would you do this? How would you do this? Well, the first claim that I want to make is that it doesn't really matter that the coin is unfair. You can use a fair coin to get probabilities of 1/2 if you need to. Any ideas how you might do this? How can you use an unfair coin to get probabilities of 1/2? How might you do this? Well, if you take an unfair coin, right, you can flip it until you get a heads tails or a tails heads, right? So you can take any unfair coin and flip it until you get a heads tails versus a tails heads, right? One of the two things has to happen, right? You do know the value. Actually, you might not even know the value of P. You don't really need to know the value of P. So I'm just telling you right now that you can convert and you can use an unfair coin to get fair coin probabilities if you flip it until you get a heads tails versus a tails heads, right? And notice the probability of both of these events is, so these are perfectly complementary, right? And that's how you can turn an unfair coin into a fair coin. Let me know if there are any questions about that. So you can convert an unfair coin into a fair coin by flipping it until you get heads tails versus tails heads. So it turns out it doesn't really matter so much that the coin is unfair. Okay, you can just use it because heads tails and tails heads have the same probability, whatever they are. So you can assume for now and forevermore that P is equal to 1/2. Let me know if this makes sense. So you can convert quite easily an unfair coin into a fair coin by flipping until you get tails heads or heads tails. So now the question is, how do you design a game where the probability of winning is exactly alpha? How would you do this? How would you do this? Okay, I seem to have stumped you, so I'm going to give the answer. And this one's really wild and quite beautiful, I think. Here's what you do. Just write the binary expansion of alpha. Okay. No, you're just waiting for the first heads tails versus the first tails heads, right? So you toss a fair coin twice, right? And if two tosses are the same, you repeat, otherwise you stop. Okay? Okay, so maybe there's some confusion on this point. So you take your unfair coin, you toss it twice. Okay? And you're tossing in groups of two. Yeah, you start over each time. I'm sorry. I hope that wasn't too confusing. You do need to start over each time. Okay, but hopefully that's clear now. So here's what you do. Take alpha and write the binary expansion of alpha. So alpha can look like point, I don't know, 1 0 1 1 1 0 0 0 1 1. I don't know. It can go on forever even. Okay. So this is the situation that I'm in. So now you can pretend you have a fair coin and basically toss the fair coin until it comes up heads. Okay. So toss a fair coin, which you can pretend you have, right? So toss a fair coin until it comes up heads. Okay. Now here's the situation. Let's say you get heads for the first time on the nth flip. So let's say this happens at the nth flip. Let's say this happens on the nth flip. Look at the nth number in the binary expansion. Okay. If this number is 1, so I can denote these numbers like alpha 0, alpha 1. Actually, I'll denote them like this. Alpha 1, alpha 2, all the way. So alpha 1, alpha 2, alpha 3, all the way, and so on and so forth. Okay? So if alpha capital N happens to be 1, Alice wins. Means Alice wins. And if alpha capital N happens to be 0, then that means Bob wins. And I claim Alice's probability of victory is going to be exactly alpha. Why is this? This is quite beautiful, I think. So why is this? Why is Alice's probability of winning going to be... So remember, you flip a coin until you see your first head, and if your first head happens at position N, you look in the binary expansion of alpha and see if the number there is, see if the digit there is a 0 or a 1. If it happens to be a 1, then Alice wins. If it happens to be a 0, then Bob wins. So let me ask you, what is the probability of Alice winning? What's this going to be? Well, the probability that Alice wins is going to be, well, let's see. She wins if you get ahead on the first flip, right? In this one. So that's just alpha 1 times 1/2, right? She does not win if you get ahead for the first time on the second one. So that's just alpha 2 times 1/4, right? And then it'll be alpha 3 times 1/8. And then alpha 4 times 1/16, and so on and so forth. But this is precisely the binary expansion of alpha. In fact, this is equal to alpha. Okay, I've sorry, I ran into chat. But this is equal to precisely, if you just keep this going forever, this is equal to precisely alpha. So that's it. That's all it takes. So there's a yes, thank you, John. So there's two rather interesting things going on here. Number one is how you turn an unfair coin into a fair coin. And I'm sorry if my explanation was confusing earlier. You flip it twice, you just start over. If you get two of the same things, and then you start over. And then you just basically do this process until you see a heads tails versus a tails heads. They should both have equal probability. Just make sure you're doing it in pairs. I guess I wasn't explicit about that before. And that's how you turn an unfair coin into a fair coin. And then this is how you come up with a game where the probability of winning is precisely alpha. I actually think this might be the most kind of like weirdly practical problem in the list that I have. So there you go. Hope you enjoyed that one. All right. If there are no more questions about that, I will move on to the next problem. Okay, so we did the airplane problem. Okay, so here's one. This is, I think we've only done one Putnam problem so far, but I do believe this is also a Putnam problem. So let me know if I'm in my own way again. I am in my own way again. Okay, I'm not going to do problem surgery again. I'm just going to put this down. So choose at random 3 points on a circle, and then compute the expected length of the arc that contains the point 1, 0. This problem is deceptively tricky because most people think, I think most people, I'll say, my confession is myself included. Most people, when they see this problem, might think, well, by symmetry, the expected lengths of all the arcs should be the same, right? So the answer should be 2 pi over 3. But that's not true. That's not true. So here's one thing I want to say that will disabuse you of the notion that the answer is 2 pi over 3. If you pick a point on a circle, on a unit circle, right? Then, for example, a bigger arc is more likely to contain it. Do you see that? So if you choose a random point on the circle, you choose some fixed point on the circle, then a bigger arc is more likely to contain it. So hopefully with that single sentence, I've convinced you that the answer is not 2 pi over 3. It should be bigger than 2 pi over 3. Okay. But how do we figure out what it is here? Okay. So you're picking 3 points at random on the circle. You want to interpret them as cuts, divide the circle into 3 arcs. What's the expected length of the arc? Okay. So how are we going to do this? Well, our chosen point is there's like a bunch of different ways to do this problem, okay? But here's what we're going to do. This is our chosen point, namely 1, 0. Okay? Now, and I have 3 randomly chosen points on the circle. So the arc that'll contain 1, 0 will have a point in the counterclockwise direction from 1, 0, and it'll also have a point kind of in the clockwise direction from 1, 0, right? You can consider it either way. It's not going to affect the answer because they have because everything is uniformly being chosen. They have like a area of 0 in the problem, so you don't need to worry about it. But sure, you can take it either way, and you will get the same answer either way. Okay, so hopefully that answers your question, but let me know if it doesn't. So you take your point 1, 0, okay, and there should be a point up north, and there should be a point down south of it, which contains it, okay? So one thing to note is that the expected length of this arc should be just twice the expected length of this length over here, like this point 2, 1, 0. I'm not saying that this picture is symmetric, but if like x is the length of this, then that should be, and let's say this is y, right? Then x, and let's say this is y, and let's say this is z, right? Then x is definitely equal to y plus z, right? X is definitely equal to y plus z. And I'm not saying y equals z. All I'm saying is that the expected value of y is equal to the expected value of z. And expectations are linear. So the expected value of x should equal the expected value of y plus the expected value of z. And the claim here is that, of course, by symmetry, the expected value of y should equal the expected value of z. So I should just need to compute the expected value of y, for example, and double it. Okay? So I would just like to compute the expected value of y. That's all I really need to do. So how would I compute the expected value of y? Well, okay, so a lot of ways to do this. One trick I'll remind you with expected values. So if you have a positive random variable, okay? If you have a positive random variable, you should just be able to integrate. So normally, for example, if you were to compute the expected value of y, you would integrate, y times, this would be 0 to 2 pi, the probability that y attains all sorts of values. So, this would be the PDF for y, dy. This is how you would normally do this computation. However, for positive random variables, there's a little bit of kind of trickery. Why you can absolutely do this problem that way, John. But actually, I'd like to point out something even simpler than this, right? So, whoa, oops. So, I want you to recall the following. In order to compute the expected value of y, I can just integrate over the range of y, which, by the way, is 0 to 2 pi, the probability that y is greater than or equal to lowercase y dy. This is a fun thing you can do with kind of random variables that happen to be positive, right? So this is a fun thing you can do with random variables that just happen to be positive. Okay, let me know if there are any questions about this formula. If you've never seen this before in your life, I'll show you in the discrete case why it works. So for example, if you're computing the expected value of a discrete random variable y, right, you would be, let's say, adding from y goes from 0 to infinity, y times the probability that y equals y, right? Also, I'm running into myself a little bit. But you'll notice there's one copy of the probability that y equals 1, 2 copies of the probability that y equals 3 in this sum, 3 copies of the probability y equals 4 in this sum. So if you break this sum down, it's equal to, like I said, there's 1 copy of the probability that y equals 1. There's 2 copies of the probability that y equals 2. And then there's 3 copies of the probability that y equals 3. But if you just look at this, so there's, like I said, there's 3 copies of the probability that y is 3. So you get this like weird triangle sum of probabilities, right? But if you look in this triangle on the, I'm running into myself again. If you look in this triangle on the first row, the first row of this triangle is just the probability that y is bigger than 0. The second row of this triangle is just the probability that y is bigger than 1. The third row of this triangle is just the probability that y is bigger than 2. And that is why you can compute the expected value of a positive random variable by just adding up the probabilities that you are greater than values, or just integrating over the probability that you are greater than certain values, okay? So now my question is, if that's true, what is the probability that y is greater than or equal to lowercase y for some number? what is this going to be? Any ideas for this one? What's the probability? So this is just the probability that there's no point chosen with an angle between 0 and lowercase y. Agreed? So this is just the probability that not a single point, it's even easier than that. So this is the probability. So the probability that y is greater than or equal to y is the same as the probability that not a single point was chosen. Right. With angle between 0 and lowercase y, right? With angle between 0 and lowercase y. Yeah, that's exactly right, John. So it will be, I believe, hold on, I think you need to divide by 2 pi cubed in your formula, John, because the probability, right, all the way around should be, yeah, I think you're close, but you need to you need to scale down by 2 pi. You need to scale your random variable down by 2 pi. So I believe the answer here should be, and I'm pretty sloppy. You can check what I'm doing, but I do believe that this answer should just be. So there's a probability that of the 3 points, not a single one was chosen between 0 and y. So this will be, yeah, there it is, John. It's 1 minus y over 2 pi quantity cubed. That's exactly right. So you're just integrating, this is just 1 minus y over 2 pi quantity cubed, which you don't even need to do, so Zuza, you don't even need to do parts here. You can just u sub this pretty quickly, right? So I don't know if I want to bother with this. So you can u sub this really quickly. Let me just open Mathematica because I've forgotten the answer. So this is just the integral 1 minus y over 2 pi quantity cubed. Need to make sure 2 pi is nicely in the denominator. What did I? Oh, it should be between 0 and 2 pi. It's just pi over 2. Right. So this is just pi over 2. That's the expected value of y, which means the expected value of x is actually pi. How cool is that? So this is pi over 2. If you just multiply it by 2, you get that the expected length here is going to be pi, not 2 pi over 3. So my initial guess for this one was also 2 pi over 3. By the way, this is not the only way to do this problem. I just think this is the easiest way to do this problem. So hopefully that makes sense. And there we go. I don't know what else to say about it. So let me know if there are any questions about this. So the final answer here should be pi, because the expected value of y is pi over 2. So the expected value of z is pi over 2. So the expected value of x should be pi. And that is the answer here. There it is. Okay, I hope you enjoyed that one. So let's, I believe I have one more problem in store for you guys. And let me know how you feel about these problems. I picked them because I like them. So hopefully you enjoy them too. So let's see here. Yeah, here's one. Might need to do like more problem surgery to get it to actually fit on the screen. Okay, it did not fit on the screen. Okay, so here's the final problem. So there's 64 teams who play a single elimination tournament. So there are 6 rounds, and you earn points based on kind of what round you make a correct prediction in. So every correct prediction you make in round 1 earns you a point, and every correct prediction you make in round 2 earns you 2 points, every correct prediction you make in round 3, 4, every prediction in round 4, 8, and then I believe you're up to the semifinals. So after that, every correct prediction is 16 for the semifinals, and if you predict the finals correctly, you're at a 32. And so the question is, what is the expected number of points here that you are going to get in this scenario? What's it going to be? So let me know if the question makes sense. Hopefully it seems fairly reasonable. So how might you solve this one? And so I hope you're all thinking of, those of you who are thinking about it, I hope you're all thinking of linearity of expectation, because it is a great way to deal with stuff like this. So I hope you're using linearity of expectation, indicator random variables, and so on and so forth. I hope if you've heard of these things before, I hope thoughts like that are flowing through your mind right now. Okay. All right, I'm about ready to get started, so let me know if you guys are good, and let's go. So there's 64 teams playing in the tournament. So of course the question is, I would like to break down my winnings, right? I'm trying to compute the expected value of my winnings. And it would be nice if I could break down this random variable W into a sum of random variables, okay? So here's what I'm gonna do. So why don't I break it down as follows? So essentially, for each game, let's define an indicator function based on whether or not I get points in that game. Okay, so I define this indicator. So the indicator for a game is 1 if I get points on the game, and 0 if I don't get points in that game. Okay? So the indicator for a game is going to be 1 if I get points on a game, 0 if I don't get points on the game. Which means my winnings for the game will be 2 to the round that the game is in times the indicator random variable for that game. Okay? So this is my indicator random variable for my game. All right. So this is 1 if I get points in the game. In this game, right? And 0 otherwise. Okay. So the indicator random variable for this game is 1 if I get points in this game, 0 otherwise. So let me ask you something. Of course, the expected value of I game should just equal the probability that I get points on the game, right? So it's just the probability that I get points in the game, right? What is the probability that I get points in a game? Well, in order to get points in a game, I need to predict that game correctly, right? But I must also have predicted every game leading up to that game correctly, right? So in order to correctly, in order to earn points on a game, I needed to correctly predict its winner, which means I must have correctly predicted the winner in all of the previous rounds, right? So all of the rounds that kind of led up to this game, right? So the probability that I get points in this game is just going to be 1/2 to the round that the game is in, right? So this, I mean, hopefully that makes sense to you guys. So this should just be, the probability of getting points in a game should just be 1/2 to the round that the game is in. Hopefully this function round of game makes sense, right? So the probability that I get points in a game should be 1 over 2 to the round that the game is in, because in order to get points in a game, I must have predicted accurately the things that led up to that game. Agreed? But how much... So, of course, the expected value of the winnings is just the sum. Like, I need to add up, right, for all the games, right? I need to add up the winnings on those games times the probability whether I won them or not, right? So the winnings on a game are just like 2 to the round that the game is in minus 1, right? Because I only make $1 per one game in round 1, right? And so on. So, and I make $2 on the games in round 2. So the winnings is for every game, I need to do 2 times round that the game is in minus 1 times the indicator value for the game, because I might not win any money if I don't predict the game correctly, right? So I get that the expected value of my winnings should just be the expected value of this random variable. But now I'm done, because what does this tell me? The expected value of my winnings is just going to be the sum over all the games, right? 2 to the round that each game is in, minus 1, divided by 2 to the round that each game is in. So I'm adding 1/2 for all the games. You see that? Because this cancels, this is just a half. How about that? So for every game, I'm just adding 1/2. So just 1/2 times the number of games is the answer. So this is just 1/2 times the number of games. That's wild, huh? Let me know if there are any questions about this. So the expected value, the probability that I make money on a game is 1 over 2 to the round that the game is in. And the amount of money I make in a game is 2 to the round that the game is in minus 1. You multiply those two numbers, you always get a half. So the expected value of my winnings will be 1/2 times the number of games. Amazing, huh? Hello, Brian. All right. So this is just 63 over 2. And that's it. So that's all you're going to get out of me today. I hope you guys enjoyed that. And let me know if you have any... Yeah, that is amazing. I agree, Ken. I agree. So I hope you enjoyed that. I tried to pick good problems, and I hope you enjoyed them. So you can catch me again on Wednesday. And thank you, Petros. I always appreciate your numerical simulations. You're so fast with those. Will you post these puzzles in the description? Yeah, I can do that. That's fine. And then those are all pretty good. Thank you. Thank you, John. Thank you so much, everyone who showed up. I will catch you all on Wednesday, I hope. And I'll see you then. Bye-bye. Peace.